So our first speaker is Rosalind Picard. She's a professor at MIT, at the MIT Media Lab, which she's also chairman and chief scientist of Affectiva, which is a company working in the area of biomarker development. Really important to point out that Roz has played a very important role here in the autism community, having founded the Autism and Communication Technology Initiative at MIT. She started the first course on autism at MIT and has really been dedicated to people with autism, helping them to build better opportunities for learning and communication, helping build relationships, and that's really what her company is all about as well. Roz? I don't know if it works in that.
Thanks. It's a pleasure to be here. We'll do the little laptop shuffle here. I have a conflict of interest to disclose. As Rob mentioned, I have a spin-out company, Affectiva, where I serve as chairman, chief scientist, and co-founder, so have some equity and other involvement in my consulting time free from MIT over there. Otherwise, let's see if this is working. We have a little tangle here. Sort of like neuronal networks with all these wires. We have, but I am full-time at MIT, although I'm on sabbatical right now, which means I'm not teaching, and gives me a little bit more time to do some basic research, interact with the people that I want to learn most about. Today, I'm going to dive in on some work that's not just my own team's work, but also work of others on autonomic measures that are objective, repeatable, reliable for understanding autism and things that are very commonly found in autism. I want to start with a brief story. I often attend this retreat called Autreat. I don't know if anybody here has ever been there. It's a wonderful gathering arranged by autistic people who actually choose to be called autistic. They've even written why they don't want to be called persons with autism. It's by autistic people for autistic people and their friends and family. And it's a very comfortable environment dominated by autistic people who sit around and talk about what they need, really, to live better lives. And it's wonderful for those of us developing technology to get invited to this, to be up alongside them and try to really understand what we need to do to help them have better opportunities to learn and overcome some of the challenges that they face. While I was at lunch in this very comfortable environment, one young adult on the autism spectrum said the following. She said, "I'm going to be reevaluated soon. I can behave more autistic or less autistic. How autistic should I act?" All right now the measures, as you've seen, even with the new DSM-5, they're observational, right? There's somebody looking at how you act. And we all know that an individual that you get to know on the autism spectrum can have times when they act very autistic and can have times when they actually act pretty comfortable and social, honestly. If you've really gotten to know somebody, you'll see the eye contact turn on or off. So we want to look for something that isn't just a short-term observation dependent on how somebody acts. We want to truly understand what's going on long-term in real life. And as we look for measures that work in real life, not just in like a 30-minute lab visit or an expensive short fMRI session, but that really carry with you in real life, we have some challenges to face because a lot of the work that's been done doesn't port to real life. Now, there are portable EEGs. I've worn them around Boston and endured the stares. People looking at me. You know, when you're an MIT professor, you're allowed to wear a lot of crazy stuff. And some of these look like they were developed by MIT professors, especially that crazy one up there on the right. And there's a lot we can learn from the EEG. Don't get me wrong, I'm not dissing this. But to get to fully real life, what's going on from morning to night, I think we need to go beyond this. Also, it's fascinating too because we want to look at emotional changes, emotion dysregulation, what's leading to that irritability, what's leading to the shifts that are modulating the behavior. And often that's got emotional drivers underneath it. We can't get that from an EEG right now. We don't reliably get affective information from the EEG. We get that from deeper subcortical structures. So some of the promising fMRI EEG stuff is interesting, and especially coupling that, I think, with autonomic physiology is extremely promising and interesting. And now it is possible, with a variety of technologies that have been coming on the market, to start to get some of the components of autonomic physiology that are related to some of these deeper controlling affective brain structures continuously and comfortably in regular all-day life. We have thousands of hours of data from individuals now to demonstrate this. And so comfortable now that people sometimes walk off with the sensors, forgetting to return them. Now, here's just one. This is probably my most complicated slide. Bear with me a second here. I'm going to make it very simple for you. See if I have a pointer. Oh, oops. No, let me go back. So we have the autonomic nervous system. It has three branches: the sympathetic, the parasympathetic, and the enteric. That's not shown here. The enteric is your gut brain, also extremely important in autism and understudied. Let's talk today mostly about the sympathetic and the parasympathetic. Both of these innervate pretty much every organ in your body, and this complicates our attempts to measure these systems. So take the heart, for example. I'm going to make an analogy to a car engine. Now, so if your heart is revved, it's like the car engine being revved. Fortunately, unlike the car engine, your heart doesn't just shut off, hopefully, like when you shut off a car. In fact, your heart is constantly revved. You might say it's actually pre-revved higher than your resting heart rate right now. And what happens is the parasympathetic component acts like a brake on it, slowing the heart rate. So your resting heart rate is usually slowed by this vagal brake. When your heart rate goes up, it could be because the foot has been taken off the brake and the heart rate goes up. The engine's revved. That's a fast way to rev it. Another way to rev it is to put your foot on the gas, on the accelerator, and that's more analogous to the sympathetic system. This is sometimes called the fight or flight, sometimes called the rest or digest, although they're both quite a bit more complicated and interesting than that. So when we try to measure something like the parasympathetic component, we actually can do spectral analysis on the heart rate variability, pull out the high-frequency component, and get a good estimate of that parasympathetic component. But right now, we can't get a good estimate of the sympathetic component from analysis of the heart rate. It's confounded. Fortunately, there is one organ that is purely sympathetically innervated. Anybody know what that is? I know some people here do. The skin, yes. So the skin gets the pure sympathetic innervation. And when we measure the skin, we are able to see a bit more of what's going on. So let's actually see if I can go to this movie here and show you an example of the skin conductance being read live from a girl on the autism spectrum. Here she's having a little bit of a meltdown outward. This also corresponds to a peak in her skin conductance here. Let me explain what you're seeing here. This is a 45-minute therapy session. This is kind of cool because for the first time we could take the lab to her normal environment, her normal occupational therapy environment, as opposed to having to bring her into our lab. So she's wearing some bands around her ankles. They look like sweatbands with a prototype of our sensors in them. This work was done a while ago with the sensory processing disorder gang, Lucy Jane Miller and crew. The occupational therapist is wearing them too, but we're only showing the child's data here. She's also undergoing some other therapy with audio on her head, which confounds all the different inputs we're dealing with right here. This blue window is a zoom in of this blue strip right here. The right edge is the live streaming from her two ankles here right now. And we see her kind of decaying in her sympathetic arousal, the skin conductance, as she relaxes in the ball pit. We also we see her kind of chilling here. It's kind of going down. It goes up again when she gets out of the ball pit. It starts to go down again when she relaxes in it, again here. And here we see it peaking when she's getting on a swing. There are many things that map to this signal. It's not highly specific. Skin conductance will go up with the emotional load, with cognitive load, and with physical load. The motor planning, I've seen a person on the autism spectrum who's having trouble moving. Maybe an early Parkinson's diagnosis coming. And I've seen them think about moving their toe, and the signal goes up. And they're concentrating on getting all the muscles to move, and you can see this respond. When she swings here, we see a nice decaying exponential. Many times, although not always, we see an individual who engages in a repetitive movement, and it's associated with a huge calming of this sympathetic arousal. Very peaceful for them. In fact, I've seen them also show that to other people, like, look, let me do this, because this helps me. And there's power in that data when it's not just your word against somebody else's, but you can show them that there's a physiological concomitant change that is associated with feeling calmer in this situation. Right, so what are some of the scientific things that have been shown here? And let's look, first of all, there's been a lot of studies in sensory modulation disorder and looking at the sensory processing issues, and it's really nice to see this component added explicitly to the DSM-5. Pretty much everybody I've met on the autism spectrum complains about some sensory problem that they have that they wish we researchers would address. This is an area where you can actually measure in precise protocols like this astronaut lab protocol done by Lucy Jane Miller and crew, where the kids are in this lab and they're bombarded with, after resting for a little while, with an audio tone, with visual strobes, with siren sounds, with wintergreen fragrance, maybe sometimes that should be other fragrances, different tactile stimuli, vestibular tipping, and multiple trials of these, and then looking at their responses and seeing things like, are they over-responsive? What's a typical normative distribution of responses, and where do these kids lie with respect to this on these different measures? And we've seen some kids are extreme outliers on some of these measures. They are really over-responsive. Some are under-responsive. You do not want to do group averaging of data like this, right? You get no effect when you average everybody together. You want to look for phenotypic clusters and different specific patterns that are objective and measurable and stable with respect to an individual. And this helps us understand an individual and what they need specifically for their treatment. We also hear a lot about anxiety in autism, and I loved that Rob put that cluster up there. I highly recommend to you go on YouTube and search for Christ School 2007. That's the name of one of my favorite videos on anxiety and autism, relating it to repetitive movement disorders, including the ones that the rest of us neurotypicals do regularly, whether flicking a pen or tapping our foot, or great footage of Bill Gates during the legal hearings rocking. And how these typical behaviors may be somewhat used to deal with anxiety. Now, this is incredibly prevalent, and again, we have to look at specific individuals and measures of this that change. For example, Matthew Goodwin, who's here, has done work looking at the heart rate of children exposed to a number of stressors in a comfortable school environment that they're used to. And he found that in this study, the autism group had much higher heart rate responses. In fact, he also found kids who looked like they were very calm on the outside and at rest and at peace, with resting heart rates well above 100. All right. Now, most of you probably have a resting heart rate below 90 in this room, and when you see a kid whose resting heart rate is like, they're really revved up, and they look calm on the outside, that's when you get in their face and look like maybe you need to stimulate them a little bit more, that's a recipe sometimes for a little bit of aggressive behavior, and could be quite provoked, even though it may look like a surprise on the outside because you misread them. They looked calm on the outside, but they were revved up on the inside. We also see this with skin conductance. So the heart rate, again, confounds the sympathetic and the parasympathetic. Skin conductance, this is more a pure sympathetic look. This picture is the first time that I saw data of, in this case, an MIT student, 24/7, wearing a wristband measuring the electrodermal activity or skin conductance. And we see each row is a day of data. Lots of activation in the lab, chilling, watching TV. Sleep, it was mysterious in the beginning. I'll say a little bit more about that. We're finding consistently very large, sometimes the largest of the day, peaks during sleep. Quite interesting. In general, quite a bit of activation during an exam, quite a bit during studying, and kind of to the embarrassment of we MIT faculty, consistently low during classroom activity. Now, note too, how this person's baseline is very different from day to day. 6, 3, 9, 21, 15. A lot of different scales. What's going on here, and how do we normalize and deal with that? I won't go into detail here because there isn't time, but I want you to know we're developing methods to deal with this, and they're actually informative and interesting. And here's just a taste of some data from a study that NSF Expeditions has funded, joint with a number of amazing partners around the U.S. here, where we have gotten long-term data. Usually the norm and almost all the literature is, like 30 minutes of measurement of somebody in the lab, right? Now, 30 minutes of measurement of this person in the lab, it's going to give you a very different answer depending upon which day you picked them, right? We need to look beyond these little 30-minute measures. And here is 60 days of all day at school for 5 kids on the autism spectrum. And right away we see some very different distributions. And this is just the average data. There's a lot more sophisticated, interesting stuff. We see these 2 kids have similar distributions. That's interesting. What else do they have in common? Is this related to something that we can use to give them more efficacious treatment? These also have similar distributions, right? A high day for this kid is below average for this kid, right? I mean, these are really different profiles, and they are objective and measurable, and we can start to take this and relate it to what's going on in their life and what treatment they're on, and see how these things shift. We do see them shift with medication. I mentioned that we saw huge peaks during sleep. You may or may not know, but half of parents who have a kid on the autism spectrum report that their child is a bad sleeper. What does that mean? Well, it probably means that nobody slept well last night, and they're kind of wondering. And if their parents actually slept, maybe the kids slept. And it's very hard to have an accurate read of who's sleeping and how well and what's going on. And my understanding from the doctors we've worked with here is the way they treat this is they start with a list of medications at the top, and they work their way to the bottom and just see what works. What they wish they had instead is some measurable objective patterns of each of these sleepers that they could start to relate to which treatments work and don't work. So we started this collaboration with Dr. Beth Mela at Vanderbilt. Now we have collaborations with Chuck Seisler and Bob Stickgold here working on larger sleep populations. And here's just an example of the skin conductance in a boy on the autism spectrum who it's actually going up before he falls asleep here, and it's quite high during deep sleep. He has almost no REM, and he only has this very high frequency skin conductance during his first phase of deep sleep and not during the other ones, which is kind of atypical for what we've been seeing in our broader typical populations. We need a lot more normative data before we can say more, but there is some very interesting findings starting to come out of this. We're also seeing some interesting asymmetries. Usually the left and right do the same. I was asking Beth Mela after looking at some of the data, is it possible that like half of the brain could be in one sleep stage and the other half in the other? I mean, in a human? Like, is this really possible? Because I'm seeing it look like one side is in one stage and the other side's in another stage. And she said, yes, that actually is possible. In fact, it's also possible for parts of the brain to go asleep and not other parts in autism. So we are seeing some of that brain activity reflected when we measure at multiple points on the body. And we want to understand this for an individual, what this means and how we can use that information to give them better experiences. We're also very interested in how these can be validated as intermediate measures or as predictive measures. And I have a really cool finding I want to share with you here. It's just appeared in 2 medical journals with two different pieces of very interesting findings. And this story starts where one of the guys in my lab he has a little brother on the autism spectrum, and over Christmas break he said, hey, can I borrow a couple of your sensors to take home if you're not using them in studies over the break? Because my little brother can't talk, and I want to read out like when his level's high, what's stressing him, what's frustrating him. And I'm like, sure, take them. Back then they were still full of wires, and I had to send him home with a soldering iron in case one of them broke. So he had them, his little brother was wearing them on both sides, mostly because we thought one of the sensors might flake out on us back in those early days. So I'm looking at the data over the holiday, and at one point, one afternoon, I see one side has this gargantuan peak, totally off the charts of anything I've ever seen in our lab, even with strobes and obnoxious sounds and big exams and stuff. And the other side had like almost nothing. I went looking, and there's like a little blip there, but I would have just thought it was noise if I hadn't seen the other side. And I'm zooming in on this data going, gosh, it looks like a sensor broke. There's just no explanation for this. I've never seen anything like this. And after a long time staring at it, where the data actually looked fine before and after this huge peak, in fact, it looked like the boy went asleep afterwards. It had a characteristic sleep curve. I called him up at home. Hey, how's your holiday going? Sorry to interrupt you at home. Hey, do you have any idea what happened to your little brother on December 26th at 4 o'clock? And he says, I don't know. I'll go check the diary. And I'm sort of holding my breath, hoping that he wrote something down in the diary then, right? Because we all know what happens with diary studies, right? They mostly get filled out in parking lots. They're really unreliable. But this was an MIT student, and he had taken good notes. And he comes back and he says, that was right before he had a seizure. And I thought, oh my, that's interesting. Next thing, being in this amazing Boston area community, I was able to call another undergrad's dad, Dr. Joe Madsen at Children's. Dr. Madsen, hi, my name's Rosalind Picard. Is it possible that there could be a huge sympathetic surge right before a seizure? And he said, that's interesting. Well, maybe. We've had some patients who have like hair standing on end on one side of and on just one side of the body, hair standing on end on one side of their body, or auras or other kind of weird feelings that precede seizures. So anyhow, fast forward thousands of hours of data later, IRB approval in a study in Joe's lab measuring EEG, ECG, EDA, electrodermal activity on both wrists, and video around the clock. We got data that really kind of knocked our socks off from a signal processing standpoint. You don't need to go looking for needles in haystack with this. The peaks are enormous. This is just examples from one boy who has 3 convulsive seizures here. The doctors labeled all the seizures blind to our data, just using their standard epileptologist practice. This is the boy's sleep here. Don't know what this is. This is the movement. We also measure accelerometer, actigraphy, get the repetitive movements, get the jerking, the seizure. And long story short, we have gone on and shown a lot of things, 2 of which I'll highlight here. One is we were able to build an automated detector that's more accurate than just the accelerometer-based detector, and it's more than 94% accurate and fewer than 1 false alarm per 24 hours. You might be curious when the false alarms tend to occur. They had a Wii game in the hospital. Lots of excited jerking, if you've seen kids play Wii, and also a lot of kids flapping. So we, would want to couple that with a little bit more sophisticated recognition of those cases to further reduce those false alarms. But it's already much better than anything that's out there. We also were able to show that something else that I think is really important. And one of the things I didn't realize, epilepsy rate is 90% in Rett syndrome, 70% in CDD, and estimated to be like at least a quarter of all folks on the autism spectrum, sometimes believed also to be underdiagnosed because a lot of the seizures might be being missed on the outside. We have detected things with the wristbands that look like a seizure when the EEG may not pick it up, and that is consistent with studies that have shown direct stimulation of subcortical structures can elicit EDA. There could be a subcortical seizure that does not spread to the cortex, and we pick it up, and the EEG may or may not. I just want to mention something that I was kind of stunned by here. I didn't realize that in the U.S. 2010, there were more deaths due to seizure-related consequences than breast cancer. Epilepsy is on the rise. The most common cause of death in the children and adolescents is officially called SUDEP, sudden unexplained or sudden unexpected death in epilepsy. And one of the reigning biomarker hypotheses for what is perhaps causing it, although it's not proven, is that the brain waves after the seizure, so they kind of go crazy during the seizure, then they're suppressed. They go below 10 microvolts for a long period of time. And if they stay flat for a long period of time, that's dangerous. Now, that's a biomarker that you need an EEG to get, and it would be an important one if your child happened to be wearing an EEG all day. But a lot of people on the autism spectrum and with epilepsy don't want to walk around in daily life wearing an EEG. So is there another biomarker that we could give them that tells them this? And to our surprise, we found that how long the brainwaves were suppressed was highly correlated with the amplitude of the response of the sympathetic arousal as measured on the wrist. So this then can be a kind of a proxy for this potentially dangerous event in the brain. It's even more interesting than that. It's not just the sympathetic arousal that was kicked up, but I mentioned that vagal brake, right? To keep your heart in the right range, you need something that's both kind of revving it appropriately and slowing it down appropriately. And this is the the vertical axis in both of these is the duration of brainwave suppression, which higher is worse. More skin conductance, worse brainwave suppression. Worse brainwave suppression, less vagal brake. So it's like the accelerator is on and the brake is withdrawn. I mentioned, too, briefly that there was this asymmetry. We're also finding now there are a number of brain imaging studies that have shown asymmetric amygdala development, like greater right amygdala with social phobia, also asymmetries related to pain and depression and certain kinds of anxiety. And we are now running studies with left-right, and we are seeing some very interesting asymmetries that are appearing to be consistent with some of this brain imaging literature. So again, what's pretty cool is what we used to have to do, with direct brain imaging, we're now getting correlates of on the body in forms that are much more convenient to wear long term. All right, I think I'm near the end here. One last slide that's an example of using this in a drug trial for measuring responsiveness. This is ongoing. I can't say too much about it right now, but some of you know the trial going on with Rett's syndrome at Children's Hospital right now, and I thought they were very pioneering to also want to look at these objective behavioral physiological measures. They're measuring the skin conductance, the accelerometer activity, and the skin temperature. From these, we can find the seizures that are happening in the girls, we can find the repetitive movements, we can find the sleep patterns, and we can get objective measures of these before, during, and after treatment. And even if the Rett's isn't entirely cured, if we can show a decline in the repetitive movements, a reduction in the stress and anxiety profile, an improvement in the sleep, then that would be significant, believable, objective measures of progress that we'd all like to see. So thank you very much, and I think we'll be taking questions. Yeah.